Okay, you guys. So apologies for not being there with you today. Mixcora let me know that this is where they left off on Monday, and so I'm going to pick up here and run through some concepts here with the air pollution chapter, and then I'm going to leave a couple things for the end for Friday. So we'll leave ozone depletion and the stratospheric ozone layer issue for Friday, as well as indoor air pollution, looking specifically at radon as an example of that. But just picking up here, starting with looking at this comparison of PM 2.5, that's the fine particulate matter. You can see here in this heat map, LA has a pretty serious problem with PM 2.5. That's the average annual concentration. So this is not just a snapshot of one day, but this is kind of the values for the entire year. And, the Bay Area has a problem as well. It's certainly not as severe as Los Angeles. Okay, I won't spend a lot of time on this. This is something you're seeing in the graphs, just a comparison between the US EPA standards for air protection, air quality, and then looking at how China categorizes theirs. So, the numbers are really the important thing here. We can see that we're looking at September of 2020 here with these values. These are for Portland, Oregon, when they're having really intense wildfires. And these are extremely hazardous PM 2.5 values in particular. And this gives you a little more information. There's an entire plume all along the entire west coast of the United States associated with those wildfires. Okay, a little further back, 2018, you could see, cities in California had some hazardous days. Sacramento here, not too many, but definitely some days with larger orange slice, unhealthy for sensitive groups. And that's certainly, concern for people that are elderly or may have pre-existing conditions such as asthma or emphysema. Just looking at more data here, Washington, D.C., you can see the air pollution values here, looking at, again, PM 2.5 and a comparison over the same time period with New Delhi in India. So, our Clean Air Act has led, and we'll discuss that a little more here, but it has led to some really amazing advances and protection of our air. So, okay, some of the dirtiest cities for air quality, top 3 are here in Southern California. Well, Phoenix, Arizona, and then contrast that with some of the cleanest. So Honolulu, cleanest air. Florida has some clean air as well. They get regular precipitation and sea breezes coming across that peninsula that keep their air fairly clean. Okay, what are VOCs? So volatile organic compounds, anything that has a smell is basically the result of a VOC, something that's aerosolizing in molecular form, getting into the air, and we can detect that, with our noses. So paint is we looked at this a little bit, but paint is certainly something that has VOCs in the structure and the paint itself, and VOCs are kind of given off into the room as someone paints in a really intense plume, and then over a period of time even after the paint dries. So you can look at any can of paint. This particular Harmony brand from Sherwin-Williams has 0 VOCs, so that's kind of a green or ecologically friendly paint. This is really good to use in the house. Here's a different label here, I should be clear, and you can see that if you check the label on paints, there needs to be, in all paints, there's a label that tells you the amount of VOCs, volatile organic compounds, that are present in the paint. And some of those can be harmful, right, to human health. So, all right, VOCs are important because they're not just found in paint. They're in, again, anything that has an odor. And we have lots of smog in Los Angeles, so you guys are familiar with that. There's basically 2 major delineations for smog. There's gray and brown. Gray smog is primarily from industrial manufacturing of goods or burning coal to create electricity. And brown smog, which is what we have in Los Angeles, really from automobile exhaust, creating some secondary pollutants in the environment around us in Los Angeles, and creating that brown haze that we're all familiar with. Okay, so just looking at the chemistry, study this a little bit so you're familiar with it. This is LA smog or brown smog, also called photochemical smog. So it happens where you have a sunny place like Los Angeles. Certainly, any city with a lot of sunny days is going to have some smog formation, a brown smog formation. But LA is unique in that we have a ring of mountains around the basin, Los Angeles itself, that kind of trap that pollution. And we'll look at that thermal inversion. So here you've got a primary. So look here, right here, primary pollutants and secondary. So primary are the orange pollutants in the boxes. These are primary. They're given from the source and not changed at that state. And then secondary pollutants form in the atmosphere above us when those primary pollutants react with other molecules in the air. Okay, so here's NO2 or NOx, right? NOx. Oxides of nitrogen emitted from both natural and anthropogenic sources. Some of these are from our cars. Some of these are from industrial processes, manufacturing. And what happens is in the air in Los Angeles, these NOx will react with oxygen and form ozone. And we've said already, earlier, ozone is bad at ground level. It's bad for human lung tissue. So this is a secondary pollutant. We don't like it in any high levels. You've seen that in the lab that you did. But what can happen here, if we look down below, is that we get the formation of ozone in this sunny condition. But then you can have the NOx also react with VOCs that are being emitted. Not just from paint, but industrial processes, anything that you can smell, even gasoline, right, at the gas stations. That's why we have those vapor. You might not be familiar. We haven't discussed it, but there's California has vapor catch nozzles specifically installed at gas stations to catch those vapors and keep them from escaping to the atmosphere and adding to the smog problem. And some other states do not have that. And so we're lucky that that's something that's been required. At any rate, NOs and VOCs form photochemical oxidants as a secondary pollutant. And together, the ozone and these oxidants create that brown smog. Okay, and some days is worse than others. Some days the smog actually gets carried out over the ocean and distributed or dispersed. And some days it actually heads in through the, depending on the prevailing winds, through the Inland Empire out into the desert, Palm Springs area. Okay. So again, sulfur-based smog or the London smog, more like fine particulate matter from burning coal, and then LA smog, the brown smog. Okay. The unique part about our geography is that we get these thermal inversions here. It's basically a sandwich of warm air in between two layers of cooler air near the surface and cooler air in the upper atmosphere, kind of sandwiching that warm air and kind of trapping all the pollution relatively close to the surface. So here's that situation. So normal condition during the day, you get solar heating of the ground and warm air rising up into the atmosphere where it cools off. The higher it goes, the cooler it gets. But at night, we can get this inversion that sets up, and sometimes it'll persist in Los Angeles through part of the day, where you have cool air at the surface, cooler at night, big temperature shift from day to night in LA, and then relatively warm air that's been rising through the day, but getting trapped underneath this layer of denser, cooler air sitting on top of it. And so if you graph it, it looks like this. As you go higher up in the altitude, temperature increases for a bit and then decreases. And here's where the highest temperature point, that's where the pollution accumulates. And some of us live in that zone. Another graphic just showing the same thing, just to reinforce it. So cool air mass sinking down from the mountain. Excuse me. From the mountains and getting trapped near the surface underneath this warm air mass. And this is where the pollution tends to accumulate in the smog layer. Okay, acid deposition, totally separate concept, not something that we really deal with a lot in Southern California, but has been a problem, particularly in the 1980s and 90s. It's less of a problem now due to some of the technologies that we've installed in this country, and I'll talk about in a minute. But acid deposition, basically acid rain or acid precipitation, and in some ways, it's a similar process. You have primary pollutants mixing with atmospheric molecules, things like water vapor, and creating secondary pollutants. Okay, weak sulfuric acid, H2SO4, and weak nitric acid. Okay, and that rains down over cities, particularly in the northeastern United States, Maine, New Hampshire, Vermont. Those areas where I grew up had acid rain problems all throughout, my time in high school. And what does acid rain lead to? Okay, obviously lowers the pH of lakes and rivers and streams. That's going to decrease the diversity of organisms that live there. Okay, there's an optimal zone, the range of tolerance for pH we discussed early in the course. And if that pH level falls below their optimal zone, they're not going to do very well. Lower pH can also mobilize metals like cadmium, zinc, mercury, lead. They're found in the soils, but that lower pH can mobilize those metals and actually release them into the water, which can be problematic, right? For both biodiversity living in the lakes and streams, and then also for humans that might be drinking that water. And then they can damage human infrastructure, buildings, statues, that kind of thing. Okay, so how have we effectively eliminated or greatly reduced acid precipitation and also increased the quality of air in places like Los Angeles? It's actually much better air quality here if you look at the values on the graphs now versus in the 1970s and 80s. Okay, so these are all things that I'm going to walk you through over here in the next few minutes. And they're being deployed and installed all across the country. That's from that video earlier in the course. The Clean Air Act at its peak implementation used 1% of our GDP to get all of this technology installed. And it's an ongoing process. It's still happening. So this is kind of like clean coal. This is removing the sulfur dioxide from coal through a particular process by burning it in a certain way. And that sulfur dioxide, SOx, right? SO2 in this case, you're keeping that out of the air by removing it before the combustion process. So catalytic converters on cars are all required to have, all vehicles now in the United States have catalytic converters. That wasn't something that was required prior to the 1970s. And they changed the composition of waste gases coming out of the tailpipe to less toxic components. And then we'll look at, these are primarily, the last three are for industrial things like factories and coal burning power plants. And I'll show you some graphs: scrubbers, baghouse filters, and electrostatic precipitators. So first, catalytic converter. This goes underneath the automobile. Every car has one. Exhaust gas comes from the engine after combustion, moving your car forward. And it runs through this catalytic converter where the exhaust gases are converted from more toxic forms to less toxic. So now you get some water vapor, carbon dioxide, which of course is contributing to climate change, and then just N2, which is just atmospheric nitrogen, which is just what's already up there. So these are great. There's a problem because there's rare metals in these catalytic converters, and they could be sold, for $300 or $400 a piece to get those rare metals out of the catalytic converters. So the people have been going underneath cars and cutting them off with a cutting torch and then selling them. And that's happened even, I think, to some at least last year, some Campbell Hall students had some experience with that. So. Okay, so that's for vehicles, reducing vehicle pollution. Now, in industrial situations, large factories, basically you've got waste gas that's produced as a result of burning things or melting or heating things, maybe creating some form of metal. Think about like a mountain bike factory that's using an alloy to create mountain bike frames. Or literally anything, dishwashers, appliances that we use in our homes, furniture. The dirty air from the manufacturing gets forced into this baghouse filter scenario, or this apparatus. And basically it's a huge vacuum cleaner. You can just think of it like that. These are giant vacuum bags, and the dirty air goes in, all the particulate matter gets caught in the filters, and then clean air goes out the top. And so that's great. Periodically, these are shut off and the bags are shaken, and then all the dust gets collected in this hopper. So think of a giant vacuum cleaner for when you think baghouse filter. Okay, same idea, removing particulate matter and waste gases from a dirty source. So you've got dirty air. This is an electrostatic precipitator, basically a series of charged plates, and dirty air comes in, and there's an ion charge that's put on these metal plates in a large amount of surface area. And so particulate matter and waste gases get attracted to those positively charged plates, and then clean air leaves and all the pollutants stay on the plates. And then periodically they're either shaken or the charge is turned off and the material settles to the bottom and collected. Okay, and then probably one of the most common things is called the scrubber. Similar, again, dirty air comes in, it rises because it's warm, and as it rises through this large interior chamber, it's treated with a mist or shower of fresh water. And the water droplets actually adhere to the pollution, again, particulate matter, SOx and NOx. And all that kind of sludge now, because it's kind of a liquidy pollution, gets collected. And then there's a filtration system to filter the water and filter the pollutants from the water. And that may be removed. And again, clean air comes out the top. So when you look at these, they're large, right? Scrubbers are huge. This is a coal burning power plant, and these are scrubbers designed to shower the waste gases and remove pollutants. Okay. So the Clean Air Act, 1972, required that technology be, adopted and implemented. And there's been, a slow rollout of that across the entire country, but it is required. And so you see here wet scrubbers in 2008, and then this was projected for 2020, and we now have, significantly more wet scrubbers at power plants. This one is in power plants. Okay, that's it for today. Thanks for hanging in there with the video. I'm going to run through we just have a little bit left. Stratospheric ozone depletion. And so remember that when we talk about ozone, we say good up high, bad nearby. So, we need ozone in the upper atmosphere. It protects us from skin cancer. And down at the surface where we live, we don't want ozone because it's harmful to human lung tissue. So we'll talk about that on Friday. We'll talk about a little bit more about legislation and efforts, and then we'll also talk about radon, which is a carcinogen that can be found in certain parts of the country in buildings. Okay. Thanks, you guys.